Hello, I'm Ricard Peralta, Senior Researcher at CTTC, and today I will be making this demo about applying security service level agreements in V2X network slices. This is a showing demo between CTTC and University of Murcia in the scope of the Inspire 5G Plus project. So to begin, we have this index. First, we will introduce the ACA vehicular scenario. Then I will detail about the security service level agreements. And finally, we will see how to apply these security service level agreements in a vehicular scenario with different network slices. That will be our demo. So let's start with anticipated cooperative collision avoidance vehicular scenario. You can see that we have this cross-border anticipated cooperative collision avoidance scenario. We have two objectives. We want to anticipate dangerous events, and we want to facilitate a smoother and more homogeneous vehicle reaction. So imagine that we have this cross-border scenario. So we have an administrative border with different administrative domains. You can see that we have two different vehicles. One vehicle has some issue, so it needs to report this using a DNM message. We'll see later how these messages look like. The idea is that the newest MEC talks with a public cloud, which is able to forward these messages to all the other vehicles which are nearby. So in this case, vehicle A is able to receive this information and to react on time. So this kind of setup is necessary in cross-border scenarios. So you can see here some of the 5G requirements for this kind of a scenario. We can observe the network latency needs to be below the millisecond. The data rates uplink is quite low, and the downlink is also quite low, but the reliability in both uplink and downlink needs to be quite high. So if we focus on what's happening from the V2X communications perspective, we can observe that one of the most important components of this architecture is the message broker, which is responsible for this distribution of CAM and DEM messages. The CAM messages are the cooperative awareness message. This incorporates the position and the tracking of each of the vehicles. And then we have the DNM message, which stands for Decentralized Environmental Notification Message, and it's used for all the alerts. So all the successes that happen and need to be reported. CAMs are periodical, so we have a CAM message each couple of milliseconds, and we have a DNM message only event driven. So we can see that it is very important that the message broker, which is responsible for sending all these notifications and messaging to all other parties involved. So we have in our case we are using MQTT protocol. MQTT is a lightweight and simple messaging protocol, which is based on a subscription publishing model and was designed for constrained devices and low bandwidth. It has been used extensively in IoT applications, and the central entity it's called MQTT broker, which is responsible for message delivery. We consider a cross-border scenario that involves multiple operators running different MEC applications. One application might be this MQTT broker, and thus we are applying a hierarchical MQTT approach to the vehicular message brokering. So we have a parent-child architecture, as we will see later on. First, but I want to detail a little bit and explain more details of this onboard unit application. This allows us to that's the software running inside the car, and allows us to notify and send and receive these CAN and DNM messages. This OVU application can be deployed on a general purpose computer with has external connections to the GNSS receiver and the control area network bus of the vehicle. So we obtain all the information directly from the vehicle and from the GPS signal. This OBU application can be configured on an Linux system that's based on V2X, and it incorporates all the protocol stack for ITS C5. We have tested this OBU application with real cars. So if we take a look how this application is composed of several independent software modules that communicate each other using a synchronous messaging library. You can see that the web interface is a graphical user interface that acts as a human-machine interface. We will later show this view from the demo, so we will see how a car perceives all the demo from the web interface. Then, of course, below there is an HTTP server, which facilitates the communication of the web interface to the rest of the modules of the OBU on board unit. We have a registration and authentication, the DNM service module, which is responsible for this encoding and decoding of DNM messages. It's important that we can generate DNMs through when we want to generate alerts, and that's something that we have also available on our onboard unit. The CAM service is the module that's in charge of encoding and decoding the CAM messages, serving as location updates for this vehicle tracing, the beacon service, and for all the other vehicles. The CAM messages are triggered periodically, and the position of the vehicle is provided by the GNSS module. Then we have the V2X message manager, which is responsible for the encoding of all the protocols in UDP packets and so on. GPS service module connects the USB to the general external CNS receiver to obtain all the position updates. And that's it from this OBU application. In this slide, we can observe a DNM message. So you can observe, for example, the position in the DNM message within this management container. Then we can have also the situation container, which informs of the event type and the information quality. And finally, we can observe also the type of the message and the timestamp. So this is how we report alerts messages with specific event situations. This is the hierarchical architecture that we are using in our demo. So we can observe that we have two different MQTT brokers, the child 1 and the child 2. And also we are deploying a parent MQTT broker in a public cloud. This is very significant because this architecture allows us to have this multi-domain cross-border scenario. That's something that in the Freischlick Loco, for example, we are studying. So you can observe how the workflow for this hierarchical approach of MQTT brokers is run. So you can observe that we have two different phases. First, the initialization phase, where the child MQTT broker subscribes to the parent MQTT broker, and then later on the different clients connect to each own respective child MQTT. Later on, if a client generates a DNM message, this message is notified through the complete chain from the client to the child 1, for example, that goes to the parent and forwards it to the next child MQTT broker, which finally sends it to the OBU2, which was subscribed before. So this is the procedure for this hierarchical approach, and we think that it's very valid, and we have previously demonstrated that the protocol overhead of this approach is very low, so it does not affect the KPIs related to the scenario that we are presenting. So this is how we observe this the first phase, the subscription phase, and then the running phase. So you can observe that the timestamp that the time that the protocol requires to forward one MQTT message from one child MQTT broker to the other child MQTT broker is very extremely low. Now I would like to introduce the security service level agreements, and that's something that we will present in the next slide. So we know that the service level agreement is a contract between a service consumer and a service provider, which defines the quality of service given by the second to the first. Now we want to introduce the concept of security SSLA, which looks towards the service security aspects of a service. The design security manager aims to use the specs SSL model. This specs SSL model was first introduced by Casola et al. In this conference, and it's being studied in most of the different projects. For this SSL, we have one example. So we include each SSL includes security controls. So, for example, one of the security controls could be the multiple factor authentication. It uses metrics. So we have the number as a metric, the number of factors used for authentication, and the SLO, the objective, the service level objective, equals to 2. So in this case, the SSLA is proposing a multiple factor authentication of equal to 2 factors used for an authentication. This model has been extended to support network slicing. So we have slice resource providers that consider the slice elements affected by the SSLA. The slice requires security capabilities, can be so we can modify each capability is a set of security controls that are using this security service level agreement. And finally, these security metrics that they are used for defining the security service level objective. So we have the name, the definition, the measurement scale, how to compute its value, and finally how to process this SSLO. And all this is in this specs SSLA model that we are using in our demo. So you can observe here we have one slice security model that this network slicer is able to control and deploy VNF, control SDN controllers, and other technical business services. We have the SSLA responsibility to work towards this slice security model, and this SSLA is the one responsible for example, introducing new characteristics to this slice. In our case, you will see that in our demo, we are introducing one security control, that's the information system monitoring for inbound and outbound communications traffic. We introduce one metric, which is the trustworthiness. I will later detail what trustworthiness means and how it is measured. And the SSLO, this metric is between 0 and 1, so we have a very high threshold for SSLO. This means that the value that our IDS system, our intrusion detection system, receives, analyzes the different messages and detects and a stranger, the trust of this detection needs to be quite high. So we now go into the demo, we jump into the demo and how it will be performed. So we are applying what we have explained of security SLAs in our V2X network slices. So we are showing the two walls that I have previously introduced. So in this slide we can observe our misleading car accident. So first, this is our demo. We will first see this scenario where we have two different vehicles, for example, that are running in this way. So you can observe that we have deployed two different RSUs that run the two different child MQTT message brokers, and we have a central node which is running the parent MQTT message broker. So in our case, we observe after deploying our security mechanisms, we observe that we have an intrusion. We have a fake car that is notifying an accident. This needs to be stopped somehow, and we trigger this when we realize of this fake car. We trigger the blocking capabilities of our firewalls in order to remove these messages from the system, and later on we are able to return back to our previous situation where we don't detect the fake alarms, which can lead to bad behavior of the different cars involved in the demo. To do that, we are planning this functional architecture. This is how we can observe we have a firewall system in every vehicle mech. So we have the child MQTT broker and the firewall, and then in the cloud DC we are deploying an IDS as a security function. So we have this is able to receive all the different MQTT messages that are going through the parent. Here we deploy the parent, so the IDS system is able to subscribe to all the different messages and analyze which ones are from the fake car, and then this security function will notify to the intelligence engine all this information, and the security orchestrator will take a policy for blocking the fake car in the firewall. That's our functional architecture. This is how it looks like. This is the engine that's being deployed inside Inspire 5G Plus. So you can observe that we have a slice manager, we have a security orchestrator, an NFBO, which is Sonata. Then we have a security intelligence service and the policies and necessary manager. This, of course, runs on top of this infrastructure of multiple nodes and core data centers. And then below we can see how we deployed the different VNFs and the different security functions. So, slide we reproduce the animated workflow. We can observe that we trigger the policy management deployment of the different slices. So we have deployed the MQTT brokers, both the child and the parent. Then the policy manager requires the deployment of the different security functions through the service orchestrator. So we can see that the firewalls have been deployed, and also the IDS service, and also the security intelligence service has been configured in order to start monitoring the different updates from the IDS. So now imagine that we have this fake car that appears. The IDS is able to see the messages that this fake car is producing, and it notifies the security intelligence service, which is able to detect that our security service level agreement is not being, we have an issue, and it reports it to the policy manager, which later on instructs the security orchestrator to apply a new policy and to add this fake car IP address into the firewall that it has been previously deployed, in order that this fake car is completely blocked. So this is the closed loop for our security engine based on Inspire 5G Plus architecture, in order to detect and contain this threat. This is the deployment flow. So in here you can observe better what I have before shown to you. So you can observe how the slice and the CLI request is received by the policy. Then it's mapped from the high level objective to a middle level objective. This triggers the NST deployment to the network slice manager. The network slice manager deploys the slice through the NFBO. When this slice is deployed, then we focus on the security functions. The security functions are orchestrated by the security orchestrator, and they are also deployed by the NFBO. Then we have the policy necessary manager, which configures the security intelligence service so that it's able to receive the different updates from the different security functions. And then finally, we can consider that this deployment of the slice has been completely. Then we can observe the runtime monitoring flow. That's the closed loop where a security function detects sends the metric information to the security intelligence service, and then it validates these metrics with the predefined metrics. It checks if the SSLA is okay, and how if it detects a metrics violation, it notifies this violation to the policy and the SSLA manager, which consider the better new policy to be applied by the security orchestrator. And finally, we apply this policy to the deployed security functions. So if we consider the different elements that are involved in this demo, we can observe that the policy in the SSLA manager, we have it is able to configure the network slice manager. Then we have the intrusion detection system. You can observe how it is able to subscribe to the MQTT broker and analyze the different CAM and the messages. When we have a block list and a pass list of IP messages, and we notify if we have some element in the block list with these trustworthiness levels. Of course, we have this is a low, it is reach or not reach in case that the messages come from a valid or not valid car. Then we have this security engine, which performs these IDS monitoring actions, and it has the relationship to the policy and SSLA to trigger these new actions in case that we detect some security service level agreement violation. And this is the view of the demo from the vehicle on the onboard unit. We can observe, now I will play the video. In the video you will observe how we have two running cars. These cars are sending their position and CAM messages through different child equity brokers. Now a fake car is detected. We can observe that the other cars are receiving this fake car. All the engine that we have presented has been placed on place. The firewall has been configured in order to stop the messages from this fake car. So you can see that in our demo we have had all the closed loop. We have been able to detect this fake car, and we have been able to contain this threat by including this fake car to the firewall list in order to block the different messages that was sending. So this was the demo, and just to conclude. We can observe that we have presented this instantiation of this high-level architecture that has been proposed in the Inspire 5C+ project. We have presented the concept of security service level agreements. We have also presented an anticipated cooperative collision avoidance use case, and we have been able to detect false vehicular messages through a novel SSLA based on intrusion detection system. Now, as a further work, we need to automatically measure all the mean time to detect, so how we are able to notice that this fake car has appeared in our system. We need to measure automatically the mean time to contain, and also how we can automate this threat identification that right now is using this block list and pass list in our intrusion detection system. So that was all. I hope that you enjoyed the demo. Thank you very much for your attention, and I'm open for questions. You can send me them to this email address. Thank you very much.